In this video, I'm going to be talking about another approach for sentence embedding, which is based on the idea of entity-aware contrastive learning. So I'm going to be focusing on this paper in 2022. We present EASE, a novel method for learning sentence embeddings via contrastive learning between sentences and their related entities. The advantage of using entity supervision is twofold. Entities have been shown to be stronger indicator of text semantics and thus should provide rich training signals for sentence embeddings. So it's a strong indicator of text semantics. This is also important for searching biomedical text. Entities are defined independently of languages and thus offer useful cross-lingual alignment supervision. We evaluate EASE against other unsupervised models, both in monolingual and multilingual settings. We show that EASE exhibits competitive or better performance in English semantic textual similarity and short text clustering tasks, and it significantly outperforms baseline methods in multilingual settings on a variety of tasks. So this is the architecture. We get the Wikipedia sentences including hyperlinks, and we put it all into a sentence encoder. And for example, here, like any other contrastive learning, we have positive entities. Two entities are very close to each other, and negative entity, two entities are not close to each other. But in our sentence embedding, we recognize this important fact that the entities should have some distance. So it learns sentence embeddings with two types of objectives. A novel entity contrastive learning laws between sentences and their related entities. So the contrastive loss looks like this. We compare the sentences and their related entities. So this is just one objective, but the other objective is the usual thing, the self-supervised contrastive loss. With dropout noise, and the entity objective pulls the embeddings of sentences and their related entities close while keeping unrelated entities apart. So this is contrastive learning with entities. As you see, we have entity embedding, EI, E sub I, and we have sentence embedding. So sentence comes here, let's call it SI, and entity comes here. So it comes to this encoder, and depending on positive or negative pair, we can calculate this loss for any entity. So for any entity, we go through that because we have a sentence and a semantic related entity, and we train our model to predict the entity embedding from the sentence embedding. So we have a mini batch of n pairs. As you see, we have a mini batch of n pairs, and W here is just a learnable matrix weight, and tau is just hyperparameter. You can play with this. And this is similarity, cosine. It could be cosine similarity. And so we construct the sentence entity pair datasets from the January 2019 version of Wikipedia dump. We split text in the articles into sentences using polyglots. For each sentence, we extract the hyperlink entities as semantically related entities. Each entity forms a training instance for the sentence. We restrict the entities to those that appear more than 10 times as hyperlinks in the training corpus. They are converted into Wikidata entities which are shared across languages using interlanguage links obtained from the March 2020 version of Wikipedia dump. So we are working on this Wikipedia dump. And hard negative entities are very important. The introduction of hard negatives has been reported to be effective in improving contrastive learning models. And they are data that are difficult to distinguish from an anchor point. You have an anchor point, it's difficult to distinguish with the anchor point. For example, this is anchor point and this is hard negative. So it finds negative entities similar to the positive entity but yet unrelated to this sentence. Specifically, for each positive entity, we collect hard negative entity candidates that satisfy the following conditions. First, entities with the same type as positive entity, where it's natural. Entity types are defined as the entities in the instance of relation on Wikipedia. So if there are more than one appropriate type, we randomly choose one. The second one is that entities that do not appear on the same Wikipedia page. So this is the second one is very easy. If they don't appear in the same page, so that's easy to pick. So our assumption here is that entities on the same page are topically related to the positive entity and thus are not appropriate for negative data. Finally, you randomly choose one of the candidates to construct hard negative training data. For example, Studio Ghibli has a type animation studio. And one of the hard negative entity candidate is Walt Disney Animation Studios. So given datasets with hard negatives, you can create this loss function. You have representation of your sentence and then embedding of your entity, and it's very standard. Self-supervised contrastive learning with dropout noise, which inputs a sentence and predicts itself using a dropout as noise, is an effective method for learning sentence embedding in an unsupervised way. We combine this method with our entity contrastive learning. Given two embeddings with different dropout masks, for example, one is S sub I, the other one is sub I plus, the training loss of the self-supervised contrastive loss is defined like this. But this is the self-supervised loss and previous entity loss. And lambda, well, it's just a hyperparameter you can balance between the entity contrastive learning and self-supervised contrastive learning with dropout noise. And we use 1 million pairs sampled from the English entity sentence pairs. We train the sentence using this checkpoint, for example, Bert or checkpoint of Roberta, and take CLS like any other article, you see they take CLS representation as the sentence embedding. It has pros and cons, of course. You can also use convolutional neural networks for more advanced pooling, rather than just taking the CLS representation, which has pros and cons. So we compare our method with unsupervised sentence embedding methods, including the average glove embedding, average embedding of vanilla Bert or Roberta, and previous state-of-the-art SimCSE, which I've explained this before. And we evaluate sentence embedding using 2 tasks. So these tasks measure the degree of sentence embedding, capturing fine-grained and broad semantic structures.